liquid properties can be discussed and explained now that we understand intermolecular forces. So we'll talk about at a molecular level what's going on with each of these different properties. We'll talk about viscosity, we'll talk about cohesion and adhesion, and we'll talk about surface tension. Right now I just want to focus on viscosity though. So viscosity is the resistance to flow. Liquids are a type of fluid. The molecules brush past one another. They interact with each other on their way somewhere else. If you run into a bunch of your friends on the way to the huddle, or you're going to a food truck and you're getting food, it's going to take you longer to get there if you run into people you're more attracted to versus walking by a bunch of people you don't know, because you're going to stop. You're going to talk to them. You're going to stop and talk to them. Anyway, so stronger intermolecular forces mean a more viscous liquid, but as we increase temperature, that greater kinetic energy helps fluids to overcome those intermolecular forces. So honey is a viscous liquid. If you stick it in the microwave, it becomes runnier or more slack, as the British would say. Motor oil starts out a little bit more viscous when your car is cold, but then as you turn your engine on, it'll warm up. Before all of the oil additives that have been manufactured to help with performance, it used to be common practice to turn your car on for a minute or two before you even drove anywhere to let the oil lubricate and heat up so that it wouldn't be too viscous before you started to drive. That's not a big deal anymore with synthetic blends and stuff, but just kind of a fun fact. While we're on this motor oil kind of tangent, needs lubrication. It's a blend of hydrocarbons, mostly 10 to 34 carbon atoms per molecule. If you multiply the carbon atoms by 2, you'll roughly get the number of hydrogens that molecule has. So we're talking about molecules that range anywhere from 120 grams per mole to 400 grams per mole. These are pretty big molecules, so they have large London dispersion forces. As the temperature of your engine increases, the viscosity will decrease a little bit, but additives in oil will help reduce this decrease with temperature. We don't want our motor oil to get too low in its viscosity. And so the 10W30, I don't know if I'm saying that right, but it's a common multi-grade oil. It has a blend of these hydrocarbons in it as well as additives, and these numbers mean that it has a viscosity of 10 at 0 Celsius, which is winter, and 30 at 212. I'm not sure what these numbers are. Maybe it's some kind of index or comparison or a relative scale. But roughly, okay, the viscosity index, that means it's more viscous with a smaller number and less viscous with the higher number. Maybe it's a fluid flow rate thing. I don't know. But it stays within a certain range so that your car can run even when it's hot or cold. Very cool. Technology strikes again. Let me just go back and talk about cohesive forces. So, intermolecular forces between identical molecules are called cohesive forces. So, in a liquid, those intermolecular forces that the oil molecules are feeling are called cohesive forces. We'll talk about cohesion in a minute. And then at the surface of liquids, these cohesive forces between the molecules give rise to surface tension, which is what we'll be talking about next. So surface tension is a type of tension that is the energy required to increase the surface area of a liquid. And so what that kind of looks like is, actually I'm going to talk about this penny example first. So water exhibits a very high surface tension because its interactions, its intermolecular forces are so strong, such that we can see them kind of coalesce, cohese on spider webs in droplets. But surface tension is the energy required to increase the surface area. So here we have a liquid, we add it to the penny, we can get it to bulb up like this. The surface tension is, as it bulbs, it increases its surface area, and so that's the energy that it's talking about, that transition between the bulbous state to having added too much water, and it breaks that surface tension. So that energy to break it is the surface tension. So it derives from the cohesive forces between the water molecules. Some insects use surface tension to walk on water. So here's a little buggo. Not really sure what kind of bug, actually. There's a few that'll do this. And this particular one, I should look it up real quick. Okay, it's called a water strider. Cute, right? And they're actually relatively large, so they're smaller than a grasshopper, but bigger than like a mosquito or something like that. So if you picked one up, you would actually feel its weight a little bit, but they're still able to stride on the water because their legs have these little bendy things where they get enough surface that their pressure is spread out, and the surface tension of water, there's actually a normal force pushing back up, but this isn't physics, so we won't talk too much about that. But it's the surface tension that allows the water strider to walk on the surface of the water. And this is helpful for trying to navigate life between the fish and the birds who both want to eat you. Well, actually, I don't know if fish eat bugs. I imagine they would. I think they have. Certain species do. Adhesion. The interaction between two different types of molecules are adhesive forces. So cohesion is between the same kind of molecule. Adhesion is between two different things. Often it's the liquid with its surface. So if adhesive forces are less than cohesive forces, the substance doesn't spread out on the surface. It would rather stay together with itself. So water on a table or mercury will actually do this if you dribble some onto a lab bench or something. The opposite is true if adhesive forces are greater than cohesive forces. So on other kinds of surfaces where water is attracted to them, like glass or paper, water will spread out. One kind of result of this is the formation of a meniscus. So here on the left we have mercury in a glass test tube. And it's kind of hard to see the difference between these two fluids, but here's mercury and here's water. Mercury actually has a slight bulb here. It's got a surface tension to it. So this is concave. I guess it depends which angle you're kind of looking at it from, huh? Versus kind of convex. And that's because Mercury has higher cohesive forces between the mercury atoms than the adhesive forces between it and the glass. Whereas water has great adhesion between the water and the glass, and so it kind of creeps up the glass tube on the sides all the way around the circle because it's attracted to the glass. And what this forms is the meniscus. And so that's why we always take readings at the bottom of the dip, because these adhesive forces can change depending on how clean the glass is, whether there's surface problems with it. It's less repeatable than where the meniscus falls, and harder to read. Similar in idea is this concept of capillary action. So we're still talking about adhesion and cohesion, but adhesive forces allow capillary action to occur. What is capillary action, you ask? Let's see, do I have the actual definition in the slide? I do not. But basically it's the ability of a fluid to rise based on adhesive forces, surface tension. It fights the force of gravity, like literally. So you could drip paper on a surface and hold the paper towel straight up on it and just touch the edge of it, and water would still climb up the paper towel, and that is capillary action, because the fibers and the water molecules are attracted. Most of these are electrostatic interactions, some kind of dipole-dipole interaction. The adhesive forces between materials is strong enough to cause upward movement against gravity. So this is also how the xylem and phloem of plants work. There's, different fibers, different, I'm not a plant biologist, but the water can climb up to the leaves because of capillary action. In a laboratory context, we can compare water and mercury. Because water has high adhesion with the glass and mercury does not, it gives us a nice contrast to see, oh, capillary action occurs with water. So if I put in this narrow tubing, dip it in the water, over time water will climb up a little bit, not all the way, but enough such that the force that it's attracted is equal to the force of the gravity pulling down. But mercury, it's the opposite. It experiences capillary repulsion because it would rather be with more mercury. Its forces, its cohesive forces are stronger than its adhesive forces in mercury. Alright, we're going to do it. Last slide of this section. Just kind of an application. You don't need to know this for the exam, but a lot of medical tests require drawing a tiny amount of blood, and they use these things called capillary tubes. So this is a capillary tube. The liquid flows up. It's water mostly, so it adheres to the glass. You prick your finger, that drop of blood holds together because of surface tension, and then the narrow glass tube, called a capillary tube, is touched to the drop of blood, and it climbs up on its own. And it's actually really cool to watch this happen with fluids, not so much with blood, but whatever floats your boat. And then the large surface area also helps with the adhesive forces. Alright, I forgot one more thing I wanted to say.